today we have, so as a first speaker, we have Luis Alvarez. And I think Jacques has a few words to introduce our first speaker. So please go ahead.
Yes, alors, welcome. Bienvenido a la conferencia de Pierre Magal. We will speak a bit English. I knew Luis Alvarez and Jean-Michel Morel probably 25 years ago. They were at this time playing with image processing. Now I see that they have built a variational model for computing the effective reproduction number of SARS-CoV-2. It's a very important problem. We are working with Pierre and Quentin on this problem too, and we will be very interested in this conference, please.
Okay, so thank you very much for the introduction and for the invitation. It's my pleasure to participate in this seminar, and this is a joint work with Miguel Colom and Jean-Michel Morel from the Université Paris-Saclay. The main goal of this presentation is to introduce a new technique to estimate the effective reproduction number RT. The content of the presentation is organized in the following way. First, we will introduce the renewal equation, which link the incidence curve with the effective reproduction number and the serial interval. Next, we will introduce the EpiEstim method, which can be considered currently as the reference method to compute the effective reproduction number. Next, we will present the method we propose based on a variational technique. We also address the problem of the weekly administrative noise due to the way each country counts the number of cases every day of the week. We will show the functionalities of the online implementation of the proposed method. And finally, we will present some conclusions. The renewal equation links the incidence curve with the effective reproduction number and the serial interval. Nishimura in 2007 proposed this formulation of the renewal equation, where the number of new cases is expressed in terms of the new cases and the effective reproduction number in the past and the serial interval. In what follow, we will name this expression as the Nishimura formula. And in fact, most of the work we are going to present here is based on the comparison of the actual incidence curve and its expected value using the Nishimura formula. To compute the effective reproduction number using the renewal equation, this formulation is usually simplified, assuming that the effective reproduction number is locally constant. In the simplified formulation of the renewal equation, the term RT minus S is replaced by RT. So we assume that the reproduction number is locally constant, and we arrive to this simplified version of the renewal equation. So by solving this simplified renewal equation, we arrive to this naive estimation of the effective reproduction number. And here we have the same expression right in a discrete way. But the point is that the lack of quality of the data makes this naive expression unuseful. It means that it's not appropriate to compute the actual reproduction number. So next we will present the EpiEstim estimate of the effective reproduction number, which can be considered as the current reference method to estimate the effective reproduction number. So Corey et al. In 2013 showed that if the incidence curve IT follow a Poisson distributed model, which mean the simplified version of the renewal equation, that is the mean is given by this expression. So if we assume that the mean is given by this expression and that the effective reproduction number is constant in a time interval of size tau. And we assume that the effective reproduction number is gamma distributed with a gamma of parameter A and B. Then the posterior distribution of the RT tau, this is the effective reproduction number is also gamma distributed with the posterior mean given by this expression. And in fact, this expression represents the formula to estimate the effective reproduction number by the EpiEstim method. So the default value of the parameter are tau equal to 7, that is the size of the time interval, and A equal to 1 and B equal to 5. These constant values for A and B has very little effect in the estimation of the effective reproduction number, except when the daily number of cases are very small. In fact, we can show easily that if A and B are time variant, we assume that A and B are time variant and satisfy that the mean of the gamma distribution given by I multiplied by B satisfy this equation, we will have that the posterior distribution has the same mean. So, in other words, if we, under this assumption, we can remove the parameter A and B from the EpiEstim estimation. In this work, we use 3 different serial intervals proposed in the literature for the COVID-19. We use the one proposed by Du et al., the one proposed by Nishiura et al., and the one proposed by Ma et al. As can be observed in the figure, these serial intervals are quite different and can have negative values. That is, there are secondary cases that present symptoms before the primary case presents symptoms. This non-positivity of the serial interval is measured using this expression. So we add the negative value of the distribution. So we obtain that in the case of Du et al., the non-positivity is quite significant. In the case of Nishiura et al. Is very small. And in the case of Ma et al. Is small but significant. Next, we will present the proposed variational model to estimate the effective reproduction number. So first, we extend the original Nishiura formula to the case of non-positive serial intervals, just by changing the limit of the integral in order to have that we evaluate the Nishiura formula in all the space, and in fact, what's happening is the actual limit integral are given by the support or the serial interval. So we propose to estimate the effective reproduction number using this variational model where we have 3 terms. And to simplify the notation, we assume that the analysis starts at t equals to 0 and finish at the current time that we denote by Tc. So the first term of this variational energy, or this energy, force the Nishiura renewal equation to be satisfied as much as possible. So P90 is just a normalization factor, which we use the 90th percentile of the incidence curve. And it is just a normalization factor in order to energy be independent of the size of the values of the incidence curve. So to evaluate the Nishiura formula, we need to to add some boundary condition in the case the time is lower than 0 or higher than the current time. So we assume for R, for the effective reproduction number, we assume that RT is equal to R0, RT is equal to R0 for T lower than 0, and RT equal to the last value of the effective reproduction number at the current time when T is bigger than TC. For the case of the incidence curve, we assume that the incidence curve follow an exponential, the cumulative number of cases follow an exponential growth initially. So we assume that initially the incidence curve follow this exponential growth, and we extrapolate the value of the incidence curve following this assumption. On the right part, when T is higher or higher than the current time, we use just a linear extrapolation using a regression model based on 7 days. So in this way, we can evaluate the Nishida formula in all points. The second term forced the effective reproduction number to be smooth by minimizing the distance between the consecutive values of the effective reproduction number. So WT represents the weight we assign to this regularization process. So in fact, we choose a regularization weight, WT, which depends of the size of the incidence curve given by the convolution of the incidence curve by Gaussian kernel, and of one parameter W0, which is a parameter of the algorithm. In fact, this is by far the most important parameter of the algorithms, because it's the parameter which controls the regularity of the obtained effective reproduction number. For instance, in the EpiEstim method, the regularity is controlled by the size of the time interval where the effective reproduction number is assumed to be constant. With the last term, we can use any a priori estimate of R0 as the prescribed value in the model. So this term is to include some a priori or extra information in some particular values of the effective reproduction number. So for instance, in the case of R0, we can easily show that if we assume that the cumulative number of cases follow an exponential growth, so we can deduce that R0 can be estimated from the exponential growth rate A and the serial interval using this expression. So we can use this initial estimation of R0 to include here, and the weight we assign to this value, the confidence, is defined by the parameter beta. In fact, we use also this term to obtain a more robust estimate of the last value of the effective reproduction number. In fact, what we do is to combine the values of several values RTC obtained using the last 3 days of estimation of the effective reproduction number. That is, we estimate for the last 3 days the complete sequence of the reproduction number, and from these 3 sequences we compute combining the last values of these 3 sequences, we compute an a priori estimate of the last value of RTC, and we use again this as a prediction of the final effective reproduction number at the current time, and we introduce this value again here to use as a prediction, and again we control the fiability of this prediction using the parameter beta. So this is a way to introduce a more robust estimation of the effective reproduction number the last day. Next, we present some experiments. For instance, here, for France, we compare the estimate of the effective reproduction number obtained by EpiEstim in dotted line and by the variational model solid line. The vertical line here represents a 9-day shift we applied to the EpiEstim estimation to fit the result of the variational technique. We can observe a good agreement between the results of the variational model and the one of EpiEstim shifted 9 days. Here we present the same experiment for the United Kingdom, and again we observe a good agreement between the result of the variational model and the one of EpiEstim shifted 9 days. Here we present the same for Spain, and we can observe that the final value of the effective reproduction number for EpiEstim is this value here, and for the variational method is this one, which can be quite different. No? Finally, we present the same experiment for the United States of America. In this case, we can observe a very good agreement between the results of the variational model and the one of EpiEstim shifted 9 days. In this case, the evolution of the EpiEstim estimate is quite smooth. The reason could be that the population of the United States of America is much larger than in the rest of the studied countries, and this may produce that the evolution of the new cases is more regular, and therefore the EpiEstim estimate is also more regular. As can be noticed in the experiment, we can observe a shift between the EpiEstim estimate and the one obtained by the variational technique. There are two reasons for the existence of such shift. The first one comes from the renewal equation formulation. When in the Nishimura formulation we replace the term RT minus S by RT, in fact, we are replacing the term by the value of RT in the extreme of the interval. And this is going to introduce a shift. In fact, we can expect approximately a shift about the mean of the serial interval, approximately. For instance, in the case of the Ma et al. Serial interval, the mean is given by 6.7. Another reason to have a shift is that in EpiEstim, we assume that the effective reproduction number is constant in the last 7 days, or that depends on the value of tau, but in general is 7 days. And this assumption is going to introduce also an extra shift. So in this table, we compare the optimal shift computed by minimizing the results of the effective reproduction number estimation using the variational technique and the EpiEstim technique, but changing the shift. So if we optimize the shift by minimizing the root mean square error, we obtain this value for the days of shift and this value for the obtained root mean square error. So for instance, in the case of the United States of America, we have a shift of 8.33 days, and a quite small root mean square error given by this value. So next we address the problem of the weekly administrative noise. In a lot of countries, there is a weekly administrative noise introduced by the way the number of new cases is counted. During the weekend, fewer tests are carried out and there is a delay in the registration of cases. That introduces a very particular noise. For instance, in the case of Germany, we can observe that systematically the number of cases is underestimated on Monday, which corresponds to this value, and is overestimated in Saturday, which corresponds to this value. So we can observe a clear weekly periodic pattern. The point is how to capture this periodic behavior. Our main assumption is that a significant part of the difference between the incidence curve and its evaluation using the Nishimura formula is due to this weekly noise, and we will assume that the ratio between the evaluation of the Nishimura formula and the incidence curve follows a 7-day periodic dynamics. In this figure, we show in black the original incidence curve and in blue the evaluation of the Nishimura formula. What we propose is to correct the incidence curve using a 7-day periodic multiplicative factor in order to the corrected incidence curve is as close as possible to its evaluation using the Nishimura formula. So here we have in blue the result of the Nishimura formula, and our assumption is that the difference between the actual incidence value and its approximation using the Nishimura formula is produced by this weekly noise, and we can correct it by multiplying this value by a factor which depends on the day of the week. In fact, in this figure, we plot in red the ratio between the evaluation of the Nishimura formula and the original incidence curve, and we observe a clear periodic behavior. So we see the red pattern, we observe a quite clear periodic pattern, and in black we present a periodic approximation of this of the actual ratio, and we can observe that in fact it's quite close to the original ratio. So this is the base of our approach. So to capture this 7-day periodic dynamics, what we do is to minimize a quadratic error between the evaluation of the Nishimura formula given by this expression and a correction of the incidence curve that we obtain by multiplying the incidence curve by a vector in a periodic way, where this symbol, the percentage, correspond to the module operation. So to define the way we remove the noise using this approach, what we have to find is 7 values which correspond to the correction factor we apply to the incidence curve in order this incidence curve be as near as possible to the evaluation of the Nishimura formula. So to this minimization problem, we add the constraint that the total number of incidence cases in the period of analysis, we use a period of analysis of 8 weeks. So we assume that the total number of incident cases in the period does not change after correction. So we assume that the global amount of cases does not change. In other words, what we do with this denoising procedure is to redistribute the number of new cases, but without changing the global number of cases. So in fact, once the 7-day periodic pattern is computed, we can remove the weekly noise from the original incidence curve by multiplying by this correction factor, and we can again from this new corrected incidence curve, we can compute again the reproduction number using the variational method. So we can enter in an iterative procedure where we iteratively update the incidence curve, the reproduction numbers, and the correction factor. So with this iterative procedure, at the end, we obtain the final version of all these values. So we use as efficiency measure of the denoising procedure the ratio of the root mean square error after and before the application of the weekly noise removal. So if this value is small, it means that the country is well adapted to this procedure of denoising, to this denoising procedure, and it means that we can reduce significantly this kind of noise. For instance, for Germany, in this figure, we plot in black the original incidence curve, and in blue, the result of the Nishimura formula, and in green, we observe the correction of the incidence curve using the correction factor obtained using this procedure. So in this case, we have that the improvement of the root mean square error is about a factor of 0.27, which is a very good factor. And in fact, we can see that the corrected version of the incidence curve is much closer to the evaluation of the Nishimura formula than the original incidence curve. Of course, it is this is going to depend a lot of the country, because here in the case of Germany, if, as in the case of Germany, a country counts every day the number of cases in an orderly and systematic way, following the same protocol each week, we can expect a high reduction in the root mean square error after the elimination of the weekly administrative noise. But of course, it's not always the case. Next, I will present the online interface that we have implemented, where anyone can test our methods to compute the effective reproduction number and to remove the weekly administrative noise. So in this online interface, the user can upload his own incidence curve and his own serial interval using this option. And in general, you don't need to change the algorithm parameter, And this algorithm, the main algorithm parameters are, the first one correspond to the parameter W0, which is the parameter which control the regularity of the effective reproduction number. This is the most relevant parameter. The second parameter is the weight we assign to the confidence of the estimate of RTC, the effective reproduction number at the current time, when we combine the information of the last 3 weeks, of the last 3 days, sorry. So with this parameter, we control if we want to use this procedure to get a more robust result or not. We have also implemented a forecast computation which is based on an extrapolation of the effective reproduction number and the application of the Nishimura formula. So here we can choose the serial interval. You can choose the serial interval here, or you can allot your own serial interval. And we have also implemented some advanced filtering option based on classic filtering, like the median window median filter or a moving average. But by default, we do not use this option. You can define also the EpiEstim offset, that's it. The shift you apply to the EpiEstim estimation to fit the variational model, and you can choose if you want to apply the removal of the weekly administrative noise or not. And finally, you can choose any country from and any state of the United States of America. So when you run the algorithm in the interface, what you obtain is something like that. So here we present the result of the effective reproduction number. So this corresponds to, in orange, the EpiEstim estimation, and in blue, the estimation using the variational technique. And here we present the result of the original incidence curve, this one, and the curve obtained by the Nishimura formula. So in this case, we have that here we present some results about the weekly administrative noise reduction. This case is Germany, and we have that a reduction of 0.24 in the root mean square error using this weekly administrative noise reduction. And here you have the parameter you have to, the correction factor you have to apply in order to correct this noise. Noise. So for instance, here you have to multiply the last value of the incidence curve by this factor, the previous value for this factor, and so on. So this corresponds to the 7 values the 7 factors you can use to remove the weekly administrative noise. So the numeric value of the estimation is can be download by using this option, where you can download a file where you can find the value of the reproduction number, effective reproduction number, with the variational technique, the evaluation of the Nishimura formula, the original values, and the variability of the last 3 days that we use to have an idea of the variation of that we can expect of the effective reproduction number in the last days. So here, for instance, we show another example of the United States of America, where we have a very good agreement between the estimation, the EpiEstim estimation, and the estimation by the variational model. But in this case, as we can observe here, we have not so clear periodic behavior, weekly periodic behavior of the incidence curve. So in this case, the value of the reduction of the root mean square error is 0.66. That is not so good, like in the case of Germany. So in general, what we observe is that when the reduction, when this reduction factor is close to 1, in fact, the factor, the correction factor are also close to 1. So it means that as we have imposed the preservation of the global amount of cases, we have something. We have that the factor value 1 is the default value when we have not a clear periodic pattern. Finally, we present some conclusions. So based on the Nishimura formulation of the renewal equation, we propose a variational technique to compute the effective reproduction number. The method can use serial interval with negative days, as it is the case for the COVID-19. Thus, it avoids an artificial truncation of the distribution. The method computes a point estimate of the effective reproduction number up to the current date. It seems to provide a more to-date by more than 8 date estimate of the effective reproduction number than EpiEstim. The method does not assume any statistical distribution for the effective reproduction number. The main assumptions are that the estimate of the effective reproduction number should follow the renewal equation, but keeping the effective reproduction number regular enough. We include this regularity hypothesis in the model using a standard technique of the calculus of variation. We propose to capture and to remove the weekly administrative noise, assuming that the ratio of the evaluation of the Nishimura formula and the incidence curve follows a 7-day periodic dynamics. We have implemented the method in an online facility where anyone can test the algorithm. So I'm going to finish here my presentation. Thanks for your attention, and I will be happy to take questions. Thank you.
Right. Thank you, Luis, for a very nice talk. So for people in the audience, please raise hand or just use the chat to ask a question, and I can give you I can let you talk with your microphone. So is there any question at this point?
Yes, I have.
Please go ahead.
Okay. Have you tried to evaluate the forecasting power of your method, for example, by retro-predicting the reproduction number in the past? What is the power for a week, for example, for 2 weeks?
In fact, what we do is what we do is very basic, because what we do is to extrapolate the effective reproduction number in 2 ways. There is an automatic way where the algorithm takes the median value of the effective reproduction number the last 7 days.
Yeah.
And we put this value 7 days in the future.
Yes.
And we extrapolate the effective reproduction number from the present to this value. So once we have extrapolated the effective reproduction number, we apply the Nishimura formula and we get the incidence curve.
Okay, but it's a linear extrapolation, no?
No, it's we use a Hermite polynomial. to
Okay,
get
okay.
a more smooth extrapolation with Hermite polynomial in order to go from the current value to the one that we fix in the future.
And who is using the online? It's about physicians. It's you have the possibilities to see.
Unfortunately, what we can see is the number of people who use, but we cannot we have no access to the profile of the person who access. Currently, I think that we have something like maybe about 7,000 tries of the algorithms.
Okay, no, it's important. It's important because you could adapt in the future to different customers your interesting method. And okay, thank you very much for your talk.
Thank you for the question.
Right, I think Jorge Velasco Hernandez had a question, so now you can talk.
Okay, thank you very much. Very interesting. A question is this: in many places, probably most of the countries, there is a serious underreporting of cases. So we are looking at an incidence curve that is based on reported cases that probably is underestimating the true curve by a factor of 2, 3, 4, depends on the country. And therefore, the inclusion of other information for the computation over RT could be interesting. I don't know if you have looked at processes or methodologies to incorporate, for example, the death rate that probably is, or the daily cases, the functions, the mortality, daily mortality. Probably also the curve depends very much on the positivity, the test positivity rate that we have in countries. In some countries, the positivity rate is 5%, 2%. In others, it's 50, 40, like for example in Mexico. As you run your thing for the Mexico case, it's very interesting. It is it is interesting because also another question is there are these super spreading events that are these gatherings that are not predicted for RT or for any methodology because they depend on specific dates. For example, in the United States was the Thanksgiving. In Mexico City, the coming one is the Virgin of Guadalupe festivity, which is on Saturday and things like that. And the introduction of these calendar dates that could improve the trend of any computation of the reproductive number would be interesting. And I know that you have only talked about an improvement, a very, very interesting and nice improvement of the EpiEstim method, but thinking about further research, the inclusion of these other indices and data, have you thinking about it? Are you planning to do something with these improvements? Thank you very much.
Thank you for your interesting question. So first of all, we in this particular paper we fix our attention in the Nisura renewal equation. So we use just the incidence curve, the actual incidence curve as are registered by the country. So, but in fact, as you said, we have they are strongly underestimated. And in fact, if we have not modelized this input, but if we could assume that the number of register are in some way proportional to the actual one, in some way we could say that the estimation of the reproduction number could work because the method is independent of the size of the value. So if you have this proportionality, the estimation of the reproduction number could be valid in some way. So another very interesting point is how to incorporate extra information like death as you quote, or some specific date in the analysis. No? But we do not explore this kind of interaction, but we think that it can be a very interesting approach, a very interesting, nice thing to do. No? So I think that in fact, looking to EpiEstim is actually used for a lot of things, as the forecasting using extrapolation, or what I mean is that in fact this procedure that we propose could replace EpiEstim in any protocol that EpiEstim is used, and EpiEstim is used for a lot of more things that just compute the reproduction number.
Yes, thank you very much. Very nice talk. Thank you.
Okay, is there another question? So, so I had a quick question, if you don't mind. I was wondering, are you relying on the exact count of infected, or could you also include in the model potentially covered cases, or you know,
potentially what? Can you repeat?
Unreported cases, or missing information, I mean, on the number of cases.
I'm not sure if I understand your question. Can you repeat it, please?
Right. Sorry. So you are in the model, you are comparing the output of the Nishimura formula to the count of reported cases, right?
Mm-hmm.
Does your model already include some unreported cases, or do you rely on?
No. It's include just the registered reported cases. It does not model in any way the unreported cases. No, we do not model this important aspect of for instance, asymptomatic, which never has been counted. No.
All right. Right. Thank you. And so maybe if there is no more question, now is the time to thank Luis again for a very nice talk, and move to the next speaker. So
thank you,
Luis.
Thank you very much.
Thank you.
Yeah.